Our next speaker is Professor Dmytro Savchuk, and he will tell us about simultaneous conjugacy search problem in contracting self-similar groups.
Hello, everyone. So let me first open up my file that I would like to share. Just 1 second. I think maybe here documents. No, not documents. That should be screens. Yeah, so just 1 second. Something went wrong. So that's not very optimistic. Okay, so this is the one, I guess. All right. So can everyone see my screen?
Yeah.
Okay, great. So, well, first of all, I would like to start with appreciation to the organizers for organizing this wonderful conference for so many years. And it's always a pleasure to see everyone here and to listen for the talks and to present what I have been doing recently. And especially during this time of the war, of course, that's really important to keep these activities up so that it kind of creates sense of why we do what we have to do. I'll talk today about simultaneous conjugacy search problem in contracting self-similar groups. And so this is based on two projects. So one is joint with Delaram Kahrabai from CUNY and my PhD student Arsalan Malik, who just graduates this summer. And the other project that I will mention at the end is a joint project with REU undergraduate students who worked on REU summer project. So that's research experience for undergraduates. Project which we worked on last summer. That's Luciana Scuderi and Carrie Seekamp. So those are related projects, and it will be kind of clear the connection between them. All right, so let me start first with introduction to the problem itself. So first of all, what is conjugacy search problem and simultaneous conjugacy search problem? So, the origin for this problem, of course, it comes from algorithmic group theory, but it has applications in in group-based cryptography. So a lot of group-based crypto systems are based on this problem. And so the problem basically asks the following. So suppose we have some group G, and you have two n tuples of elements, A1 through AN and B1 through Bn, such that there is one single conjugator R that conjugates A1 to B1, A2 to B2, and so on, AN to Bn, the same conjugator for all the pairs. So the problem asks to find at least one such conjugator. So we start from two pairs which we know are conjugate, so we just have to find at least one such R. So there are several crypto schemes which are based on this problem. Probably the main one is so-called Anschel-Goldfeld key exchange, which was proposed in 1999. So Ko-Lee et al., so there are multiple authors, key exchange protocol was proposed in 2000. It's just based on not quite simultaneous conjugacy search problem, but just on conjugacy search problem with certain restrictions. And I'll give a description of the system on the next slide, just to give you the flavor. So there are some Kahrabai-Khan non-commutative L-Gamal, and there was Walnut DSA, also introduced by Anschel and Goldfeld and Atkins and Gunnings, I think, in 2017. That's one of the most recent crypto systems, which was well studied over the last few years, and that was one of the proposed digital signature schemes for NIST post-quantum competition. So just to give you a flavor of how it works, I'll just give you an example of a Ko-Lee key exchange. It's kind of equivalent to group-based Diffie-Hellman protocol, essentially, where instead of raising to some powers, we will just do conjugations in groups. So public information, so suppose we want to create a common key between two parties, A and B, Alice and Bob, and you start with a group G, which is a finitely generated group, and two subgroups which commute, right? So any element of A will commute with any element of B. Of course, the groups themselves need not be commutative, need not be abelian. So private information here, Alice just chooses a private element A in the first group, and Bob chooses a private element B in the second group. And then everything is very simple. Alice just sends G to the A, and G was a public element that was known to everyone. G to the A to Bob. Bob sends G to the B to Alice. And then, of course, they can compute. Alice can compute G to the B that she got from Bob and conjugate this by A. Of course, you're going to get G to BA. And because A and B commute, because they're coming from commuting subgroups, that's the same thing as G to AB, and which is G to the A and then conjugated by B. Right. So, and this is what Bob can compute because he has G to the A, and then B is his own private key, right? So he can compute that. So that will be their common shared secret. And of course, yeah, maybe I have to switch to regular pen tool. Okay, so to find this K, of course, it will be enough to solve conjugacy search problem. So given, for example, G to the B and G, you want to find B. Restricted to subgroups A and B. So you want to find B in a subgroup capital B, and you want to find A in the subgroup capital A, right? So that's just to feel the flavor where these problems kick in. All right, so of course, the algorithms that I mentioned, Anshel Goldfield, and this CoLE crypto system, right? So they start with some abstract finitely presented, maybe that was in the original construction, but they're generally, this need not be finitely presented, but it starts with some group. The question is, what group should we start with? So of course, if you start from Z, for example, that will not work, right? Because everything conjugation will be trivial. So you have to start with some non-commutative group. And so there are many platform groups that have been suggested and studied. So the original platform was braid groups, which was proposed in CoLE. It was also looked at by de Hornoy. And so Thompson's group were studied. I can mention Spiller and Ushakov, but other people, again, I'm not claiming that there is inclusiveness in all of the citations. So there were some semi-direct products of semi-groups were suggested by Delaram and Vladimir Spielrein. Automaton groups or self-similar groups were suggested by Grigoriev some time ago, well, actually in 2019. And there was a quite recent paper by Kahrabai, Noche, and Radara. So here we propose to use a specific approach for the class of contracting. Oh, okay, so it's probably some typo here. So we just propose to try to play with the class of contracting automaton groups and see how it's going to play out. So whether those contracting automaton groups will work well as possible platform group, or maybe there will be some deficiencies and the corresponding crypto systems will not be secure, which are built on these contracting automaton groups as platform groups. So, of course, there are lots of reasons that we want to suggest these contracting automaton groups, and I'm going to talk about them now. But before, just a quick recap. Of course, that's the benefit of talking at the end of the session, that everyone already has seen all of the main definitions about automaton groups, about self-similar groups, about contracting groups. So I'll just brush through. So we're talking about groups acting by automorphisms on rooted tree. And so they are generated by automata or self-similar groups. Again, I will skip that because we had already quite a lot. So what's important here is that every element can be decomposed using so-called Ritz recursion, where every element can be represented by its sections at the subtrees hanging down from the vertices of the first level. So that's what Zoran was talking about, what Paul Henry was talking about. Right, so the only difference is that here we are using left actions and Zoran was using right actions, so his permutations were written on the left. But again, so there are two notations, you just have to keep track what notation is used. It's their equivalent, of course. All right, so every automorphism of the tree can be written in this form, where these GIs are, if the group is self-similar, again, automorphisms from the group that you start with. And sigma G is a permutation that tells you how to shuffle these trees. All right, so of course there is a dictionary, how you can convert the automata pictures into Ritz recursion picture, right? So for example, if you are in state A and you read 0, you go to state B. That means that section on the left subtree is B. If you read 1, you go to the identity state. So the section on the right is the identity state. And so the sigma notes that we're going to switch the vertices of the first level. So we put sigma here. And so the good thing about these sections is that you can multiply them. You could take the inverses, and basically you could operate with the sections with computer. So if you have 2 of them given in the form of with recursion, you could easily compute the product. Okay, now contracting groups, just as Zoran said, so roughly that means that once you go down, you start from a self-similar group and you go down the tree, the length of the sections will shrink, right? And that's one of the definitions. So if there is some constant lambda, multiplicative constant lambda less than 1 and additive constant c greater than 0, such that there exists some level L, such that for all vertices at that level, the length of the section will be strictly less than the original length of G, multiplied by this constant lambda less than 1, and maybe plus additive constant c. So that's one definition, basically, which justifies the term contracting. There is another equivalent definition, which could be stated as a proposition once we give the definition above. So the group is contracting if there exists some finite set nucleus, called nucleus N, such that for every element, starting from some level, if you go down deep enough, all sections will be of this G in this finite set N. All right, so that's set nucleus. Now, why that's important? Because that gives us a different way to represent elements of contracting groups. So now benefits. So first of all, these groups are very nice from computational perspective. They have polynomial time algorithms solving the word problem. So they have natural normal form equivalent. So in all of the preceding platform groups, normally elements of the groups were transmitted by words. So not everywhere, but in most of the cases, for example, once you start with some finitely presented group, like braid group, then you transmit the elements as words, right? And then once you could transmit the elements and their conjugates, right? So then you have to scramble somehow those words using relations. And sometimes that scrambling doesn't work really well. For example, it doesn't change the length, or maybe it's possible to recover somehow the conjugator from the normal form, right? So here we use an equivalent of a normal form. We're not going to be sending the elements as words. We're going to be sending them as so-called contracting portraits. We're going to talk about those. So there is no general algorithm to solve conjugacy search problem or simultaneous conjugacy search problem. So those groups have no free subgroups. That was the result of Nekrashevich. And so that means that they are good against so-called length-based attack. And so that's what we're going to actually study. They're embeddable in finitely presented simple groups. That's a quite recent result. Well, maybe this one is not quite recent, but there was recent results also by Colin, who is present here, and Jim Belk and Francesca Matucci, and maybe Jim Hyde, maybe, but probably Colin can correct me about Boole conjecture on hyperbolic groups. So some groups are nonlinear, so they cannot be represented as matrices. So they have a potential to withstand algebraic span attack, and that was the attack developed by Ben-Zvi, Kalk, and Saban in 2018. Okay, so how do we send the elements over the open channel? So instead of sending them as words, we suggest to send them as using their nucleus portraits. So what is that? So you take an element of your group. Let's say this is Grigorchi group, ACABAD, right? And then you develop it until you get to the nucleus. Grigorchi group is contracting with the nucleus consisting just of generators and identity, so A, B, C, D, and 1. So you take your element, you decompose it until you get to the nucleus, and then you forget the words themselves that label the intermediate vertices. You just remember the permutations at the corresponding inner vertices, right? And then you remember what are the leaves. So you erase these gray vertices and you just remember black vertices and the permutations, and that is the nucleus portrait of an element. It completely describes an element. So if two elements have the same portrait, if and only if they're equal. Right? So what are the benefits? So first of all, as I said, they uniquely define element G. Then they're computable in polynomial time in the length. They take approximately the same memory as the word itself, because the depth is logarithmic with respect to the length of the word. So you could do fast calculations in a group without the word, just using the portraits. You could multiply two portraits really fast using recurrent algorithm. And so in particular, it hides the word, even it hides its length. So from the depth of the portrait, from the number of leaves of the portrait, it's really hard to tell what the length of the word or of the original word was. So we propose to use these portraits as an analog of the normal form for elements of contracting groups. Okay, so now a natural question is, okay, given a word, you can construct a portrait. Can you go back? So maybe all of this construction is useless in the sense that if you have a portrait, it's really easy to recover the portrait, recover the word that you started with. So generally, the answer is it's not easy. So what we prove, that's probably the most theoretical result of this project, that you can actually do that. Not exactly, but so let me get into the details for regular branch groups. Again, so regular branch groups were defined already by Paul Henry, and so mentioned by Zoran and mentioned by Grigorchuk as well. If you have a contracting self-similar regular branch group that is generated by some symmetric set that contains the nucleus, then we construct an algorithm that, given the nucleus portrait of an element G, and we assume that this element G can be defined by a word of length at most n, right? We don't know this word, but we start from some portrait of an element that we know comes from a word from length n. We want to recover maybe that word or maybe some other word that also defines this G. So we construct an algorithm that constructs a word in the generating set S of polynomial in n length. So we are not guaranteed that we're going to be constructing exactly the same word that we started from. So we're going to be constructing much longer word usually, but the length is bounded by polynomial in the original length. And that word will represent the same element G. So the complexity of this algorithm is again polynomial in this original length n. So basically, you can recover some word in case of regular branch groups, but that word still will be quite different from the original one. All right, so now we implemented this construction, and we tried to play with so-called length-based attack against simultaneous conjugacy problem. So the attack here is quite a general attack, which was introduced by Hughes and Tannenbaum in 2000. And so there are various variants studied by these people, many of them. So the idea is very simple. You just try to iteratively reduce the length or complexity of this expression here. So you take the original AI from the first tuple raised to some conjugator R, and then multiply by the inverse of the element from the second tuple. So if R is the actual conjugator that conjugates AI to BI, then of course this length of complexity will be 0, right? So we start from, for example, R being identity, where you get some complexity, and then you try to iteratively gradually reduce this complexity to 0, and if you manage to do that, you found your conjugator. So usually it deals with the normal form of elements of a group, but of course we could apply this here once we do not talk about words at all, right? So we propose to use portraits as normal form, and the sum of the depth of the portraits of this AI to the RBI inverse will be the measure of length or of the complexity, right? So you take a bunch of portraits and you compute those AI to the RBI inverse, and then you measure the total sum of the depth of the portraits and see for which R this depth reduces a little bit. If you found one, you add something else to this R, try to reduce it even further. That's the idea. And we played with this attack tried different parameters. And so let me just report a little bit on the results. So for example, for Grigorchuk group, so if you do 30 runs on the number of AIs is just 5. So we have two 5 tuples, AIs and BIs, which are obtained from AIs by conjugation by some element, R. And so here we take, for example, length of this conjugator to be 30. We see that the percentage of success is really small. So for Grigorchuk group, it doesn't work. Once you take the conjugator length 100, it doesn't work at all, essentially. For some groups, it actually does work, but those groups are contracting with a very specific structure. This is virtually a abelian group, virtually Z. So then in similar settings, you actually have some reasonable chance of success. In 70% of chances, you can actually recover the conjugator. So you could try to apply for a larger tree. So for example, we played with universal Grigorchuk group, so which acts on a 6-array tree. So for this group, we have that essentially there was some small chance of success, but the problem here is that we couldn't handle any long conjugators at all. If on the previous slides we were talking about length of conjugator to be of the order 100, here we only managed to do a conjugator of length 7 because it takes too much time for this tree that branches too much. Right, so there are some complications once you take groups with acting on larger trees. Okay, so of course I'm not giving all of the results, just some. So second project is the one that I was working on with Luciana Scuderi and Kerry Seekamp last summer. So we tried to approach to implement a different attack, which we call bounded length attack. So what's the difference here? So first of all, we restrict ourselves in that project just to the binary tree. And second of all, we also make an assumption that we know the length of the conjugator. So this is not quite simultaneous conjugacy search problem in its pure sense, but it's a reasonable assumption once we talk about cryptosystems, because normally you know the parameters. You assume that you know the parameters of the cryptosystem, you know the length of the key that was used. Okay, so the idea here is a bit different. So we want to recover the action of the unknown conjugator level by level by passing from a conjugacy system for the original conjugator R to conjugacy systems for its sections. The idea itself is not new. So that was the idea to solve the conjugacy problem for Grigorchuk group going back to 1990s by Leonov, Vershkov, and Grigorchuk and Ushakov recently constructed a linear time algorithm to solve the conjugacy problem in Grigorchuk group. So Grigorchuk group is one of the few groups in which conjugacy problems can be solved in linear time, quite surprisingly, actually. So what's the idea? So idea is the following. So suppose you have, let's just restrict to just conjugacy search problem. So simultaneous will come a little bit later. So we just have two elements, G and H, and we conjugate G by R to get H, right? And then you want to understand what this conjugator R is, at least what is its action on the first level. So both G and H might be either active or inactive on the first level. So let's consider the case that they are both inactive, so they both belong to the stabilizer of the first level. So because they're conjugate, that's the only option. They cannot be either one active, one inactive. They either will be both active or both inactive. So let's consider this case when they're both inactive. If the conjugator is also inactive, right? So that's its action on the first level. Then we could just take this equality and look at the corresponding sections at the first level, and we get the following. We get that the section of H at 0 will have to be conjugate to the section of G at 0 by this R0, which is the section of the conjugator at the first level. And H1 has to be conjugate to G1. So that's what actually it says here. And here I have a label 1 because I'm going to use it on the next slide. So contrapositively, if it happens that G0 is not conjugated to H0, or if G1 is not conjugate to H1, that means that our assumption, and the assumption was that R was inactive on the first level, is false. So that means that our conjugator actually is acting non-trivial on the first level. And that's why we're going to have to use the equations on the next slide to recover R0 and R1, right? So, and we can check that those are not conjugate. Sometimes it works, sometimes it doesn't, on finite levels. So we can just take the quotient in, say, for example, level 4 stabilizer, and in the quotient by the stabilizer of the level 4, and then that's going to be a finite group, and we can check if those elements are conjugate in this finite group. If it happens that they're not conjugate, then you recover the action on the first level. Okay, otherwise, if it acts non-trivially, so then you do the same thing, and then you get that the section of G0 has to be conjugate to H1, right? And you apply the same thing. So if G0 is not conjugate to H1, that means that R was acting trivial in the first level. So that's the idea of the attack, and then you use this equation once we know that R is acting trivially. You know the equation for R0 and the equation for R1. That's a conjugacy equation that you move on with. All right, so that's the idea, and so that's what I said, that we could recover if they're not conjugate by taking the quotients in the stabilizers, with respect to stabilizers. So that's just basically, because I don't have too much time, I'll just move to the algorithm. So that's the idea. So now we are back to simultaneous conjugacy search problem. You start with GIs conjugate to HIs, and we know that there is some upper bound on the length of the conjugator. So from inactive GIs, you try to recover if the conjugator is active on the first level. If there is an active GI, then we try to find relations between the sections of R. So every active GI will give you this relation. And then you pass to new conjugacy systems for sections of R and repeat the process. And continue until, so you go down, 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 until you reach the level at which you know that R has to contract to the nucleus. And you know that level because you started from the assumption that R has a fixed length. And then you go down a little bit more to distinguish elements of the nucleus on the leaves. And then at the end of the day, return the obtained nucleus portrait of R. Right? That's the algorithm. So we could do also some bootstrapping. So if you don't have enough elements, you could, in your tuples, you could actually add more elements, and somehow that increases the effectiveness, but I'll try to finish. Just giving you the results. So I'll just give the results, for example, for Grigorchu group with this bootstrapping. So if you take R length, so the length of the conjugator to be even 1000, we can recover it with 99% of chance, even for small values of the length. So even though that this is heuristic attack, it doesn't work always, but it works in most of the cases. For Basilica group, we have similar situation. It works even without this bootstrapping update, but with bootstrapping, basically it recovers. Once you have a list size 10, it recovers always. Again, under the assumption that we know the length of the conjugator. Okay, so result for Basilica group, and maybe I'll just mention that right now we are working on extension of this attack for a larger tree with the new REU project with 2 students, Fahran Bajash and Winona Wirli, who are also here. So we hope to get an update in the next revision. So I'll stop here. Thank you very much for your attention.